Hello and welcome to this course on feature engineering with Python. My name is Valentine and I'll be your instructor. In this course, we're going to follow the following structure. We'll get started with the learning outcomes, learn about the objectives of the course. After that, get to learn about what is feature engineering, why do we apply its concepts, and also when do we apply those particular concepts when it comes to just projects. After that, we'll go through a curated reading that we have already prepared. So this is the reading that you will get to go through. It contains concepts in relation to feature engineering, as well as in-depth explanations to those concepts. You will get about 10 to 15 minutes to go through this particular reading, as well as go through the quiz that will come in after to just assess your understanding of those particular concepts. Once we have finished that, the next thing will be to now go through some practice session, which will generally entail going through some notebook that we have curated. And this notebook will actually help us go through just various feature engineering techniques practically. I'll be taking you through this particular section, and we'll be going through each particular technique as well as an example in implementation, an example implementation with Python. And I'll also give you challenges to go through by yourself. We have also provided a solution notebook that will come in handy, and this is just a notebook that contains now the solutions to the practice that you will get, or the challenges that you will get during the practice session. Once that is finished, as part of the next steps, we are going to give you a project, which generally will involve you working on a real life project where you're going to apply the feature engineering concepts that we will have learned at the start of this particular workshop, during this workshop. So generally, the idea here is that you should be in a position to be able to apply those skills in a real life project, and as a result, be able to further practice and be able to have acquired those skills that will be required for you in your journey. So the idea is that you go through this project. We have provided a starter notebook, which just generally will contain some code as well as some information that will enable you to go through the course, to go through the actual project. And this notebook will contain just concepts that are not covered in this workshop or in this course, but we have also other courses where you can also get to practice some of the concepts, actually, or the concepts that you get to encounter during this particular section. So generally, once you have finished going through the project, there will also be a solution notebook that you can be able to use to just check whether you had gone through the project in a satisfactory way. So that's generally it. That is the expectation of this workshop. And hopefully you'll be able to get the most out of the learning experience as we get started. So it will be about 2 to 3 hours of intensive learning. So starting off, what are the learning outcomes that we're going to be working towards? So by the end of this course, you should be able to describe the concept of feature engineering in solving machine learning problems. You should be able to apply feature engineering techniques in solving for those problems. You should also be able to differentiate between different feature engineering techniques, as well as understand when to apply different feature engineering techniques. What is feature engineering? So feature engineering refers to that process of transforming features when creating a model using machine learning or statistical modeling. So just as one of the ways where you would use feature engineering would be assuming that you are working on a project, and a machine learning project, and your task is to build a machine learning model. Normally, you would use historical data to train a machine learning model in order to make predictions. Now, the process of preparing that training data, that data that you use to train your machine learning model, would be what you would refer to as feature engineering. You would be generally engineering or ensuring that the features that you're going to use for training are fit or are suitable for the training of your machine learning model, in an effort to ensure that it gives or it has the best performance possible. So normally feature engineering techniques are those processes or those techniques that you'd perform during data preparation. Now, with regards to these techniques, you can perform them initially, or you could even perform them after you have already created your first version of your machine learning model or your baseline model. So you could decide, let's say, first of all, to build, assuming that you're going to be building a machine learning model to make some sort of prediction, you could decide to create, first of all, a machine learning model without performing many feature engineering techniques. Then later, once you have evaluated and seen that your machine learning model hasn't met your metric of success, then you can opt to perform model optimization techniques, which feature engineering would be one of them. So you could now go back to the data, try to understand whether you can add, create more features from the existing features, or transform the existing features in a way that will lead towards a better performing model than before. So that's when you would actually perform feature engineering techniques. So during data preparation, if you would use this particular image, which just represents stages in what is called the CRISP DM, which is a project methodology when it comes to working on data analysis or data science problems, you would perform feature engineering techniques during the data preparation phase. So normally in such a project, when you're working on machine learning projects, you'd start first by understanding the problem that you are facing, setting business metrics as well as other technical metrics. Then once you have done that, you source for data, you understand the data, you exploit, you identify missing values, outliers, etc. Then you do data preparation, and then later you perform modeling, and then you evaluate whether your model actually surpasses your metric of success, the one that you had set initially. If it doesn't, then you go back to business understanding. You try to understand what you could have done differently in order to achieve your metric of success. But generally, feature engineering would happen during the data preparation phase. So there are benefits to performing feature engineering. So one of it would be, once you have trained or once you have prepared a data set in a way that it's the best, it's in the best form for training a machine learning model, then in such a situation, you enable the machine learning model to train faster. You're able to reduce the complexity of a model and make it easier to interpret, and you are able to, again, with feature engineering techniques, improve the accuracy of the model, and also reduce what is called overfitting, which sometimes would be a problem that some particular models would face. And this just refers to that concept of your model learning so much from training data that it's not able to make predictions that are far away from just from the training data set. So generally, feature engineering has benefits, and it can even help organizations be able to achieve their objectives in relation to data related goals much quicker. An example of a feature engineering or such feature engineering processes, but we will go deeper into each and every different feature engineering technique, would be, assuming that you're working with this data set, and this data set has it's the classical iris data set. We normally refer it to as the iris data set, and this data set normally has 4 columns: sepal length, sepal width, petal length, and petal width. And there's usually another variable, or another variable that we're trying to predict, which is usually a class, or which is just a flower type. But generally, assuming these are our features, the ones that we're going to use to train a model, and we wanted to perform feature engineering techniques, other techniques that we might end up a feature engineering technique that we might end up applying would be feature construction. This involves looking at the existing features and creating new data out of the existing features. So we might decide to create maybe another column that is petal ratio, which would calculate the ratio of petal length to petal width, and you can use this to just capture just information about the overall shape of the petal. You could create maybe sepal ratio, which will be sepal length to sepal width. That's the ratio. And you can provide just information about the shape of the sepal, of the sepal, of the actual petal. You could also, create another column that contains petal area. Or you could have other features such as sepal area, petal to sepal length ratio, petal to sepal width ratio, petal shape index, etc. So there are quite a number of different techniques in relation now to feature engineering, one of it being feature construction that you can apply. And as a result of that, you might even realize that you can create 10 or even more different pieces of information or different columns that you can later onwards use as part of your training. And once you have, say, performed such techniques, possibly that could help in ensuring that your model performs better. Or alternatively, it could be the first step to also performing other feature engineering techniques. So for instance, you could perform feature construction techniques, which just involves creation of just feature techniques of new features. But at the same time, later onwards, you would perform what are called feature selections, where out of the entire data set that you're going to use for training, you could identify which actually lead to model improvement and which actually lead to model degradation, and leave out those features that or variables that don't help you as a result. So that is just a quick example of a feature engineering technique. They usually called feature construction techniques, but you get to learn more and more. But now, just going a bit more in depth with regards to the different techniques that we have in pertaining to feature engineering. The general techniques that we can be able to perform when it comes to feature engineering techniques would be, if we wanted to maybe perform feature improvement, we might decide to perform maybe data cleaning methods, or such as handling missing data, handling outliers, or performing what is called feature scaling methods, which would involve just ensuring that the data lies within a certain range. There's feature construction, which on the other hand would involve imputing or replacing or even could involve actually what we have mentioned, creating new features, or it could also involve replacing categorical features by performing what are called encoding techniques. So assuming that you have a feature in your data set, just one column called gender, and it has male and female as the data, you could decide to perform replacement of those particular values to have now just numerical representations, maybe zeros and ones, etc. Other techniques would be feature selection, where you just select which features actually lead to model improvement, or and leave out those ones that don't lead to model improvement, which is one of those things that you could actually do as part of feature engineering techniques, as well as also feature learning, which just involves just automatic identification and use of features in raw data, where you use methods such as autoencoders as well as Boltzmann machines. So you can see there are different types of feature engineering techniques that we could actually end up using. Why is feature engineering important? So you might want to use feature engineering techniques in your project if you want to improve your model performance. So there are two different ways which you would perform or optimize your models. And one way would be feature engineering, performing feature engineering techniques. The other way would be to perform what is called hyperparameter tuning. However, in order to again improve model performance, you could still decide just to perform feature engineering, which feature engineering techniques which actually would end up helping you achieve your goal. So there's that. Another reason why you might want to end up performing feature engineering. So sometimes you might have possibly features which are noisy. Maybe there are quite a number of outliers in your data set. So you could decide to perform feature engineering techniques in order to help a model focus on the most informative aspects of the data. Maybe those outliers in your data set are not important, or missing values are not important, then you could leave them out. And or you could even perform feature engineering techniques in order to ensure that your model makes the most out of the data that you are going to give it for training. Again, also encoding categorical variables. I already mentioned about the example of a column, a categorical variable that could be maybe gender, or just any other variable that has classes. It could be gender, it could be countries, it could be etc. But you can perform feature engineering techniques, more specifically encoding techniques, in order to ensure that the data that you're going to be using for training of a machine learning model has a numeric representation, as opposed to just having just textual representation. So that is one of the reasons why you would perform feature engineering techniques. When do you apply these techniques? So when you're performing data processing, so initially when you are ensuring that your data is in the right format for analysis, you could perform these different techniques, feature engineering techniques. When you want to build predictive models, such as for maybe classification, regression, then you could perform these feature engineering techniques. Or when you even want to optimize existing models. So sometimes, yes, you have already have been using some models, but later you might just want to ensure that they perform even better, then you could decide to perform feature engineering techniques. All right, so at this particular point, the next thing that we're going to do is to now go through a reading, the reading which we'll have shared. And in this particular reading, you will cover what we have mentioned in an in-depth way. So the idea is for you to just have an appreciation of those different techniques that we have mentioned. Once you have gone through this reading, which should take you about 10 to 15 minutes, you can go through the quiz, and then we can take it from there. So once you come from doing this quiz, you can continue with the course, and we'll go through now the practice work. Something to note is that the reading and the quiz are part of the resources that we provide at our platform. You might not have access if you are watching this maybe from YouTube, or this course from YouTube, or from another platform that does not have those resources. But if you're watching from maybe a different platform, some platform allow us to be able to provide this, but of course at a particular cost. So if you still want access to all the resources, you could also become an Afterwork member, and you get access to all the resources. But if you don't want to become an Afterwork member and you just want to go through the entire course, seeing what these feature engineering techniques entail without a lot of practice, you can just opt to now go to the next section, where we are going to go through the mentioned feature engineering techniques practically. We have provided a sample example notebook that will just have examples of what we're going to be covering, but not the challenges. And the project, we won't include that. We haven't included that yet. So yeah, so at this particular point, just work on the reading, the quiz one. Then once you're done, you can come back and we can continue. All right, so the next thing that we're going to be covering is now the practice session. So open the practice notebook that we have shared. If you have access to the sample notebook, then that's also okay. It will help you also to go through the examples. But if you have the access to the practice notebook, then just open it up and then we can continue. So once you have opened it, the first thing that we need to do is to save this document as we need to save a copy of this document in Drive. So go to File, then save a copy in Drive, and that should have a copy that you can be able to make changes. So in this notebook, we have curated content in relation to the feature engineering techniques that we have covered in the last 15 or so minutes. And the first thing that we need to do is to run our prerequisites. So we need to import libraries that will allow us to perform feature engineering techniques. So go to prerequisites, then run the first cell. We'll import pandas, numpy, and matplotlib. Yeah, so if you see a pop-up, just know that you haven't saved a copy in Drive, so do that. All right, so once you have done that, you should be able to see that you have already imported by seeing this checklist over here. Don't worry about if you see this cannot save changes. This notebook, I'm not able to do that. I don't want to save any changes, but for you, you should be able to save the changes. So by running this cell, we have imported pandas, a library for manipulation, data manipulation, NumPy for performing scientific computations, and Matplotlib for just performing visualizations if we want. But we may not necessarily, we actually could, we will actually perform visualization at some point when we are selecting features. So once you have run that, the next thing that we're going to go through is just some feature improvement techniques. So we'll go through standardization and normalization. These are two different techniques. Just for explanation, standardization, we normally use this technique to transform the values of a feature or variable into a distribution with a mean of 0 and a standard deviation of 1, while normalization would allow us to scale data in a range from 0 to 1. So again, standardization transforms data to have a mean of 0 and a standard deviation of 1. And something to note also, normalization usually is sensitive to outliers because it just relies on the minimum and the maximum value when you calculate it. And outliers can, affect now scaling. On the other hand, if you have a data set that doesn't have outliers, you can perform standardization since it uses the mean and standard deviation, which would be robust to extreme values. So generally, that is just where you would use each and every technique over the other. So if you have a data set with outliers, just consider going for standardization. And also, if again, maybe you have a data set that has normal distribution, you can also consider, or Gaussian distribution, just consider performing standardization. Normalization does not make any distribution assumptions. So let's just see how we can be able to perform these two techniques. So once we had imported our data set, so the next thing that we need to do is to load our data set. Once we do that, we just check out the statistical summary, which is there. Then we then now perform we create our machine learning model without necessarily performing any standardization or normalization. So in our case over here, we're going to select our features. So we have these features for the ones that we're going to use for the train and test data set. And this is what we have as the label. So X is just the features and Y is just the response or the target. We then split our data set into train and test data sets, and we have features for both, for train and test data set, as well as the response variables. So for the response variable for the train data set, we store that in Y-train, and for the response variable in the test data set, we store the respective values in the Y-test. And we want the test size to have 30% of the records in the original data set, and for reproducibility purposes, we set random state to 42. Then again, we fit our models. By fitting, we just are going to be training our models. Actually, that's what we do here. Here we just importing those algorithms that we're going to use. Then we create those machine learning models with just the respective parameters, and then we decide to create we train our model, and then we make some predictions using those models, and then later we evaluate how the models performed. So if I run this, I should be able to see now the different root mean square scores for the different models. And we will note that when we are working with root mean square, we want to have a value that's closer to 0. So a value that's closer to 0 for a root mean square just implies that we have a better performing model. So for decision tree, because our decision tree RMSE or root mean square error score is 73.0, which is closer to 0, then we can say that this is actually the better performing model over these other two. So our situation here, in our situation here, we haven't performed any sort of scaling using standardization or normalization techniques. So that's what we're going to do. We're going to repeat the same thing, but now we need to take into account of normalization as well as standardization in a separate example. Let's first of all apply normalization in this data set. But before I even do that, note that before you even perform some of the techniques that we have mentioned here, you need to check for just your data's maybe normal distribution. You also need to check for outliers. You also need to handle missing values, etc. To know which particular type of technique to use. But for now, we're just doing it to just see how that affects our performance. So for our case, we're going to repeat the same thing, select our features, split our data set. But after splitting our data set, we're going to perform normalization. Then we are going to predict, we're going to train our models, which are here. We are not importing the algorithms because we had already imported them earlier. Then we make our predictions using those trained models, and then we evaluate our models. But now this takes into account of normalization, and we are going to just compare the two. So we have 218, 51, 73, 218. So a normalization actually led to the SVM model performing slightly better because 218 is closer to 0 than 228. The same case with our initial KNN RMSE score was 89. Here we have a 51. Decision tree, initially it was 73.33. Here it's 73. So nothing happened with regards to that with the decision tree classifier. So if we wanted to use maybe KNN, we could decide to use it from this particular case. But if we, in our situation, we have just seen what's the effect of normalization on this data set. And it's that it leads to better performance for the SVM and KNN models. The next thing, we are also going to apply the same for standardization. Instead of doing normalization, we now apply standardization techniques, standardization technique, which we do. We still follow the same things, selecting our data set, splitting our data set, but then we perform standardization, then we train our models, we make predictions with them, and then evaluate them. And we can see that RMSE score is 213, which is actually slightly even better. So standardization even led to a better performing model when it comes to the SVM model than it did for, did it do? No, for KNN, it actually, it did not perform as better as normalization did, because it had 57, but here we have 51, which is much more closer to 0. And decision tree RMSE, in our case over here, the decision tree RMSE is 73, and here it's 81. So actually normalization seems to have been a better case for KNN and decision tree than the SVM. So yeah, so that's it. Just work on the challenges, the first two challenges for standardization and normalization, implement those techniques, and then observe and compare the performance of those metrics, of those machine learning models, and then we'll continue to the next step. Now, moving on, feature selection techniques. Now we're going to go through the first method, which is called the filter method, where we're going to use the Pearson correlation coefficient to be able to select features that actually lead to a better performing model. So you might want to only select, say, features which have a higher correlation with the response variable than features with low correlation coefficients for those with the response variable. So let's see how we can do that. We're going to load our data set. Again, we're going to load the same data set that we used before. This data set, our variable of interest is weight. The rest of the features are just what we'll use also for training. So we check our statistical summary, and then now, by the way, we are going to just continue now with applying normalization. We won't use any of the techniques. We just use normalization for both cases, it's because we've already learned about that. But now what we are going to do, so the first thing that we're going to do is to just create our base models. So these techniques will just consider all the features that we have in our data sets. That's length 1, length 2, length 3, height, and width. And this is our performance of those particular models. And then now we can decide to apply filter methods by first of all coming up with the correlation, the Pearson correlation values for all the features. So the correlation between say something like weight and length 1 is 0.92, length 2 and weight is 0.92, etc. So what we're going to be doing, what we are doing here is just creating a correlation matrix. That's what we have done there. Then we decided to set the visualization size, the one that we want to create. We imported Seaborn, which is a statistical data visualization library for Python. And then we created a heat map, which will give us a visualization of the correlation figures or correlation coefficients that we had here. We could have decided to just create, work with the figures here, but for ease of just being able to identify them, we'll just use a heat map. So that's what we do here. And from this particular visualization, we can decide to possibly drop values which have low correlation coefficients. It's with our variable of interest in our situation is the first column that we saw, the weight. That's if there's a variable that has a lower coefficient correlation coefficient or Pearson correlation coefficient with weight, then we'll drop it. So we can look at these values. We see length 1 has 0.92, 0.92 for length 2, 0.92 for length 3. Then we might decide to actually drop this because height has 0.72, slightly not as highly correlated. But in a real life data set, you might even have lower values, might even have almost lower values close to 0. And a correlation coefficient just describes the strength of a relationship between two variables. So you might have variables A and B, so it might mean that as values of A increase, also values of B increase, or vice versa. But if the correlation coefficient value is low, maybe it means that actually means that the values do not increase or decrease relative to each other. So we will drop this height variable to see what's the effect on that. Just note these values, performance of our machine learning model. So we will leave out height when we are selecting our data. Here we had included height, but now we will leave it out and then just perform the same thing and see what will that happen, whether that will lead to a better performing model. So for SVM, initially it was 218 and we have 212, which is okay, slightly better. For KNN, we have 64 and initially it was a 51. So here actually our model performed poorly as a result of removing that particular variable. So not necessarily the case. We might decide to leave it if you want to work with KNN. Decision tree, initially it was 73 and now it's a 84. So that particular decision of dropping that value wasn't the best one for those two use cases. For these two of them, it wasn't the best case. So we might decide to just keep it if you want to go with any of these two models. So that's one particular way of just selecting features, just identifying which features have higher correlation or have lower correlation with the response variable or the target, and then dropping those ones that do have lesser correlation. The other feature selection method that we could perform is called step forward feature selection. And this just involves starting out with no variables at all when we want to just check whether there'll be any performance or increase in how our model performs. So we might start out with feature 1 and feature 2. We check how those perform. Then we add a feature 3. Did feature 3 lead to a better performance? If it did, then we keep it. If it didn't, we drop it. Then feature 4, feature 5, etc. So that's what we're going to be learning. Feature step forward feature selection. So let's reload our data set again, and then let's do that again, and then now we will select our features, all the features that we have, split our data set, still continue performing normalization. Then we are going to define the algorithm that we are going to use. This is for demonstration purposes. So assuming that we have performed, again, we performed normalization, we saw that it actually led to better performance for decision tree regressor, or the decision tree model. Then we might decide to continue applying now another feature engineering technique. Step forward, and step forward feature selection. So, and then we might decide now to check for which of the features actually lead to better performance for this particular model. So we would import the sequential feature selector class, which would be from the ML extend library that would help us be able to perform this method. So we do that, and we define an object. Like we want to define how we also want to select the feature. So we're going to use the decision tree regressor. The number of features that we want are 4. Forward, when we set this to stop forward to be true, we now want to apply this technique where we are selecting one particular, we're starting with 0 variables, then we select 1, then we select 2, select 3, etc. But if we set this to false, it's actually going to be stepping backwards. So we're going to start with all the features, but now removing one feature by one feature, checking which of the features actually lead to better performance or poor performance, and we can drop those ones that don't help. So that's what we set. We set also verbose to be true and scoring to be r squared. R squared is the other metric that we can use with higher value of r squared, or closer value to 0 to 1 as a better performing. So if you have a model with an r squared value of 0.9 as opposed to 0.2, then the 0.1 actually performs better. And CV, which will just refer to cross validation faults, and generally this just refers to a technique that we apply when it comes to ensuring that our model doesn't overfit, which means that in each and every instance that we are training our model, we are using just different test sets and training sets. Yeah, so by the way, verbose, just we would just use it for logging, to just log the progress of a feature selector to ensure that we are able to apply this particular concept as a result of that. And then we perform our feature selection technique by just simply training our value against these the data sets that we have there, X-train and Y-train. And so if I run this, I should be able to see how our model performed when we had one feature, we had 0.76, the second feature 0.9, the third feature 0.92, the fourth feature 0.93. And we can, you can see that these particular features were the features that we were able to work with. These are the features that we were able to select for that particular use case, and which led to the better performing model. And then we, again, once we have identified that, we can just select those features that we want to work with. That's 1, 2, 3, and 4. Out of all the features that we had 5 features, 1, 2, 3, 4, 5, but only 4 of the features that we wanted. We wanted the 4 best features, and it turned out to be these particular features with these particular indexes that turned out to be best. Possibly we might have gotten to have maybe other features in a different way, but these ones are the ones that actually led to better performing models, and we decide to use now those features for the ones that we identified for just training, which we do here, as well as and then later we predict to just determine the root mean square errors. So this is a comparison, decision tree regressor without step forward feature selection, which is what you see here, and with step forward feature selection. So there was a slight improvement of performance in our case in that situation. Okay, the second other method that's related, that also it's somewhat related to this other method. It's step backward feature selection. And this process, it's almost similar to the other one. So we'll just first of all start by loading our data sets, describing our data sets. Once we have done that, we're going now to apply step backward, where we start out with all the features, but now we remove one by one features to see how the remaining features, whether the remaining features will actually end up having a better performance. We do the same case. We actually use the sequential feature selector class, just as the previous one, only that in this case we set the forward parameter to false instead of true. And the rest just remains the same. So let's run that and do the same case. So once we had removed the features 4, we had 0.94, then we had identified 0, 1, 2, and 4. So using feature, as you can see initially, so in using the step forward method, we had 1, 2, 3, and 4 as the data set, as 1, 2, 3, and 4 as the features that helped us have a better performing model. But using step backward, seems we had 0, 1, 2, and 4 that features which had those indices actually are the ones that led to a better performing model. So if we check in our case over here, step backward, without step backward feature selection, we had 73.3. With step backward feature selection, we had 84. So actually, this method may not necessarily be the best one for our case in our situation. So we might decide to just we might decide not to implement this method, because we can see here that with step backward feature selection, our performance actually degraded. So it did not lead to a better performing model. And sometimes that happens. So it depends also with the data set that you're working with. Yeah, so that is something that you can be able also to work with. You will get to apply those particular concepts in the challenge that we are going to provide later. All right, moving on, recursive feature elimination. So recursive feature elimination, generally, it's a feature engineering technique that works by recursively training a model on the data set with all the features, then iteratively removing the least important features until a desired number of features or specific performance or criterion is met. So generally, you have all the features and you remove one by one, but it's almost closer. Yes, it's almost closer to step backward, but slightly different. So let's load our data set and describe our data set. Then once we have done that, we are going to apply this particular method. So we are going to select our data set, train split our data set, perform normalization, fit our model. So we are going to actually create our models. We're going to have only two, SVM, decision tree, regressors. So we are going to create those models, but now we are going to be applying recursive feature elimination afterwards to those particular features. So we want to select the two features. So assuming that we want to select the two best features for our model, then we can set that inside the RFE object, and we use the end features to select parameter. But again, for two features, we would say 3. But the reason why I would set this to 3 is because we also want to include the response variable in such a situation. So we just set it to 3. Then step 1 just means that in each iteration of the of performing recursive feature elimination, only one feature will be removed. So we'll be checking for all the features how they all perform. Then we also do the same thing for decision regressor. We train our model, then we make predictions, and then we check how our model performed. So this is let me even just so let's just run this, and we should be able to see the output. So for SVM, which actually performed really poorly than the other two methods. So SVM 350, decision tree 77. Actually, decision tree actually works okay. And for SVM, we selected, these were the best performing models, and we got this is the output. Decision tree selected features, these were the best performing features. But again, we've included with is one actually. Okay, all right, I see. So width is actually what we had. So just something to correct here. N features to select just represents, it does not necessarily represent, you don't include the response variable. This refers to selecting 3 variables that you need to use for your data set to for your model to perform better or to perform best. So in our case, we have length 3, height, and width, which actually led to a better performance for the decision tree model, which has 77. So initially, other examples, decision tree here we had 84, but with step backward it had 73. Decision tree 73. So actually for we may not necessarily perform recursive feature elimination, but we could always just try and see whether that also yields to the better performing model. But in our case, we can see that decision tree RMSE root mean square error actually is it's slightly better, but not as better as other methods. Lastly, we can perform principal component analysis. So let's load these two data sets, and principal component analysis would help you to reduce the number of variables that you're working with for your trained data set to what are called components. So say assuming that you're working with PCA, that's principal component analysis implementation for this data set, you might even have maybe 2 or 3 components which represent are representative of the initial features. So running that, let's run that. This is just how if we don't have if we haven't performed PCA, these are our root mean square errors scores. So let's just try and also do the same thing for values. Well, let's try the same thing for PCA. When we apply PCA, what happens? So we'll still perform the same steps. Then once we have normalized our data set, we can then perform PCA, which we apply on the feature set. We don't do it on the response variable, or the outcome, or the target variable. So we do that on the X-train and the X-test data set. And then we fit that, we train our model using now the 2 different data sets, which now have PCA components, which and we train that, and then we get our predictions, and then we check our outcomes. So, and we use the PCA class from sklearn decomposition module to be able to work with that. So you can see that KNN's value went to 51, actually 51.9 initially, and here it's actually did not actually lead to better performing model, but it actually did not perform well. For SVM, we had 219. Okay, it performed slightly poorly, but for decision trees actually performed better, because initially we had 73.3, but now we have 71.71, which actually means it actually performed better. So yeah, so that's generally it. That's also one of the methods that we could apply when it comes to performing feature selection. All right, so the next thing that you're going to do once you have completed working on the challenges, in this section is to go through this other challenge that you'll find on linear discriminant analysis. So far, you'll see that we have given you examples as well as challenges for the other feature engineering techniques, say something like recursive feature elimination, principal component analysis, etc. For this challenge, you just need to visit the documentation for linear discriminant analysis in scikit-learn. And the idea is that you're going to use the key lessons from the examples and the explanations in the documentation to be able to work on that. Once you have done that, just double check your solutions with the solution notebook that we have provided to just ensure that you have a good understanding of what was the expectation when it comes to applying those different techniques. And once you have done that, the next thing that you need to do is to go through this project that will also provide a resource to. The idea is that you're going to apply the same concepts that you have learned so far in working on this project on feature engineering with Python. So you end up applying some of the mentioned techniques, and we have also provided a guiding notebook that will give you the steps and hints on how you can implement the mentioned techniques. There will also be a solution notebook to help you double check the solutions that you will have come up with. So yeah, so that's just basically it. Hopefully by the end of this particular project, you will be confident enough to be able to undertake other feature engineering projects and apply those techniques whenever you're creating machine learning models. The next step in terms of the course, if you want to learn more about hyperparameter tuning, which is another method of optimizing the models that you're working with, if you want to improve the performance of those models, then you can again apply aside from feature engineering techniques, what are called hyperparameter tuning techniques. We already have a course on that, and yeah, so you could always consider that. So that's it for this particular course. Hope you are able to achieve the learning objectives that we had set out to achieve from the very beginning. So these are as outlined as shown. So describe the concept of feature engineering in solving machine learning problems, apply feature engineering techniques in solving for problems, differentiate between different feature engineering techniques, and understand when to apply different feature engineering techniques. All the best in your learning journey, and hopefully we'll be able to also go through another course together in the near future. All the best. Goodbye.